Sounds good, Craig.
Check, check. A little bit of feedback there. Anything I should do?
It'll change. Maybe move around. It varies where you
Move around? Okay, all right. I stroll around usually. If I'm moving, then I'm more relaxed. And if I start a talk with an object, I'm more relaxed too.
Introduce you first.
Yeah, no, that's fine. Yep. Yeah.
Hi, good evening, everyone. My name is Lillian Lasher, and I'm the administrative assistant here at ASRC. One of the reasons I work here is that I love science, and I especially love geology. So I brought this up with Craig Ferguson, who organizes these talks, and he suggested I reach out and invite my own speaker. It was pure serendipity that the first person I wanted to invite was both interested and closely connected with the oldest known fossilized forest in the world, which is right here in upstate New York. I'm very anxious to hear all about it, and I'm sure you are too. So please welcome Dr. Charles Ver Straeten, geologist and curator of sedimentary rocks at the New York State Museum.
Well, thanks for coming. I don't know who Charles is, though. I'm Chuck. Yep. Got a little bit of feedback here. Is it Bob over there? Or do I have to do something here? Okay. Yep. The title of this series is Falconer, but I have to admit that I'm not a falcon, or I'm not a student of falcons, but I am a student of porcupines. That's one of my big hobbies, is studying porcupines over the winters, when you can actually sometimes go out and see them. Yeah, anyway, they're very interesting animals. And on our 26.5 acres, we generally have 5 to 7 porcupines each winter. So, yeah. All right, I am a geologist. That's what I do. I think of myself as a geologist very much as, yeah, somebody who studies rocks, somebody who studies sedimentary rocks, and a person who, as I was saying to a class this afternoon from RPI that came to the museum, I'm also a reader of rocks. We always think of reading as having to do with those various squiggly lines and things that we use in different cultures to help communicate things without sound itself. Let me see about shifting this around a little bit. I read rocks, and especially sedimentary rocks. Sorry for the interruptions. And this is one that I found. I stopped by Albany Med on the way to see a friend of mine who had a surgery yesterday. And it's just a rock out of a whole bunch of them out front. I stole it. But I always like to have a rock to start with. And this is a hard piece of rock. If I went to chip it, it would be hard to chip. This is a rock that is all silica. It's all silica quartz. This is the rock that geologists would call chert, and the public would generally call flint. And this was just a rock out there on the outside of the building. This is the same stuff, of course, that native peoples throughout the world have used to make various tools, points, and things like that. This one, despite being so hard, also has all these little white lines through it. Maybe I'm going to need to stand there. And that's because this rock was in a fault zone where there were earthquakes generated. When rocks are tight against each other, but there's a crack between them, under a lot of pressure, they will hold it and hold it and hold it until it slips. And every time it slips, there is an earthquake. So this rock came out of a fault zone, along which a lot in the past, somewhere in New York probably, rocks were being broken and earthquakes were happening. Okay, Do I have a pointer and stuff? Ah, okay, I should have brought mine. Okay, then I'm gonna roll over here every once in a while. Here we are in the area. Do you know what you're looking at? Not that far. This is an exaggerated imagery from Google Earth, and we're looking from the northeast. There's Thatcher Park, and also by the lake in between them in the back. There's Burn. There's East Burn, and my wife and I live up to the east of there, going up the hill. Here's Wolf Hill, that Route 85-443 goes up along the north side of Clarksville. That's the Catskill Mountains back there. Over here is Gilboa, known for the oldest fossil forest in the world for about 100 years. And over here is Cairo, and that's the site that we stumbled upon back in 2009. Can everybody hear me fine still? Okay, okay. If there's a problem, go ahead and speak up. Just shout out, that's fine. I'm not bothered by that. Spiderweb?
Mars.
Mars?
No, it's the root system.
Yeah, very good.
I grew up in Cairo. My uncle actually owned that quarry for a while.
Really? Oh, then I want to ask you questions, because I have no idea when they quarried out the sandstones that left this exposed. That is the roots, the impression of the roots of a tree from about 385 million years ago. We'll talk about time a little bit more in a few minutes, but here's one tree, and there's another tree. And the roots of this tree go out and around it. So we know they lived at the same time as neighbors. The smaller one probably in the shadow of the larger one. All right. Oops.
Modern tree or tree fern?
Oh, this kind of tree was what you'd call, what the paleobotanists, ancient botany, ancient plants, would call a progymnosperm. So it was the earliest line of trees that led eventually to the conifers and their relatives. Yeah. But there's other kinds of trees here too, and also up at Gilboa. All right, just a nice view that somebody I went to undergrad school at New Paltz with, Joe Gianelli, who works for the New York City DEP down in Kingston. But beautiful view. This is the front wall of the Catskill Escarpment and the two big canyons that cut up through it. Well, you can only see Catskill Clove right there. But Platte Clove, the steeper of the two canyons, is just out of view there. But I love that photo. That's great. All right, so just thinking about time. In my mid to late 20s, I was a musician. I was living down in northern Ulster County. I just, part of what got me interested enough to go back to school when I was 30 was just thinking about time, the way geologists think about time. I mean, astronomers go even deeper, but thinking in hundreds of thousands, millions, billions of years, that philosophically was like, wow, that really struck me hard. Human time, we think in time in seconds to centuries. My grandma Coaster was born in 1888, and she told me stories when she was young. I don't know how old she was before she saw the first automobile in rural Iowa, rural central Iowa. But to her, the most amazing thing was to see a human walking on the moon in her lifetime. So much changed. The first 20, 30 years of her life, everything was horses and carts and things like that. 5,000 years of written human history from China goes back a ways, but that's nothing. That's thinking in human time. In deep time, we think in tens of thousands, hundreds of thousands, millions and billions of years. This is geologic time. All right, and this is a time, this column here on the left is basically Earth's history from about 4.55 billion years ago up to the current time at the zero at the top. And the colored bands up there, the Paleozoic, Mesozoic, Cenozoic, is really the history of more complex life, starting in about the Cambrian period with the first animal life, which actually occurs in the very latest Proterozoic with just soft-bodied animals. What I study is things from this Devonian period you see circled there, and that's about 420 to about 360 million years ago. The oldest dinosaurs that show up in the fossil record, the oldest dinosaurs in the fossil record, are about 230 million years. And the mammals, our relatives, came shortly after that. You know why we have such good hearing and sense of smell and pretty good eyesight? Because during the Mesozoic, our ancestors, the mammals, could only come out at night. The ecosystems were dominated by the dinosaurs and the reptiles. And so coming out at night was the way they would get by and be less chance of becoming prey for the others. Now, what do you see? And one of you can say what you said before again. This is the Shawangunk Ridge, and that's the Catskills up there. So, yeah, the Catskills. And there's a Shawangum, as I learned from some of the locals down there, living in Ulster County. And then follow this around, Catskill, Kingston, New Paltz down here, going up to Ellenville, and then way up top, Oneonta, and over to the right to Schoharie. There's the W above the Ashokan Reservoir, going to the northwest of it, northeast, is Woodstock, and then Phoenicia back there right in the higher peaks of the Catskills. That is where Gilboa is. That is where Cairo is. So this is the area we're looking at. And this is my field area these years, the last dozen years and going on for some more years yet, is trying to understand the geology of the Catskills. And that's a whole nother talk. So the Catskills, about 385 million years ago. Where are the Catskills there? Down here. Lowlands. At that time, up and down the Appalachians, I'm going to end up going too long with things, over in New England was a mountain belt. All up and down from East Greenland down to Alabama and Georgia were these other smaller continental masses colliding with Eastern North America at that time across that full distance. And it raised up a mountain belt that the people who study the mountain belt rocks and things, they say we're on the order of the Andes Mountains in South America. Really high mountains, young mountains, and a lot of mud, sand, and gravel eroding off of them as the rocks broke down and were carried, some of that mud carried as far west as Iowa eventually. So anyway, here we are right now, a little adventure here that's not related to the forest. So that's where we're at right now, in there. In fact, almost below the A, or the pin point. And this is from about 8,000 feet over the surface. And we're kind of facing to the east. Here we are again, down here. And now still about 8,000 feet up in the air, we're looking to the east. 3 times vertical exaggeration again. Okay, this is not what the Appalachians out there would look like, the Berkshires and the Greens. Not that high, but that's the Appalachians. There's Mount Greylock, the highest peak there in Massachusetts. You can see the Hudson River going up and down this way, and Albany and etc. All right. Elsewhere now, that's a nice set of mountains there. This is the Andes Mountains looking to the east-northeast, about 2,000 feet above Santiago, Chile. Again, exaggerated 3 times. There's the highest peak in this photo, Cerro El Plomo, 17,000 feet plus. And this is really what it looks like sometimes in the Andes Mountains. Big, tall, sharp points, young mountains that are still being built, not our Appalachians that have been eroding down since the last orogeny, the last mountain building episode, about 250 million years ago. All right, a little to the west, out over the continental shelf there, still looking back at the same view here, we see this view out over the continental shelf with a seaway, not too deep, like kind of the depths of the seas that we would have found covering much of the continents, including North America, during the Devonian period long ago. So this is what, if we were to jump into a time machine tonight and take a trip, about 400,000 years ago, this is what Eastern New York would have looked like. You would have had mountain belt out here, and you would have had a seaway out here. That's the rocks in Thatcher Park. All the rocks in Thatcher Park, pretty much through above halfway up the Indian Ladder Cliff to the top, are rocks that were deposited in these shallow marine seas that sometimes also extended west of the Mississippi River, and were found in the west also. Now, 385 million years ago, things have changed. Looking west, and I chose this because that's where I grew up, Des Moines, Iowa, would be part of that seaway also, as would Ohio and central to western New York. At about 385 million years ago, the coast was around the Schoharie Valley somewhere. And the Catskills would have been land. Of course, there wouldn't have been any roads or anything like that there. But I use this as an example of what the world was like at that time, with Earth's oldest known forests. And again, this image, once again, the Catskills, rivers, and floodplains off to the sides of the rivers. A big mountain belt out in New England and stretching from East Greenland down to Alabama and Georgia, with volcanoes going off, earthquakes happening regularly, all kinds of activity like you'd see in active mountain belts today. Massive amounts of sand, gravel, and mud coming off the mountains as they weathered, as they continued to be built up through the Devonian period. Really, this is one of the things that fascinated me so much about this geology stuff, is just thinking about how different things have been over time. And just great volumes of sediment. And it resulted in this stack of rocks. These are limestones like you'd see up in Thatcher Park. In fact, the rocks at Thatcher Park extend from down here and below there a little bit, up to about here. And so that's pretty good thickness of rocks. That would be over 500 meters, over a half kilometer. So, you know, I don't know exactly the translation, but more than a third of a mile of thickness of rocks up there. These are the rocks that are up in the Catskills, though. And that thickness of rocks, big, thick stack of rocks, we don't even know exactly how thick, but perhaps as much as 1.5 miles thick of these rocks deposited as all this mud, sand, and gravel came off the Appalachians there in western New England, filling in the seaway like shoveling in a mud puddle with mud or sand and stuff, and filling it to above sea level, where all of these forests could develop by the middle part of the Devonian. All right, and that's just a better image up there of what it looked like, the mountains to the west. And then there would be this alluvial plain, we call it, with rivers carrying that sediment down towards the seaway. And out on the floodplains from the rivers, sediment being deposited during big floods. And also that's where you would find these forests that we're going to talk about shortly. All right, Devonian period. This is what I really work in. This is what I got interested in, living first in northern Ulster County and going out and looking at things in my mid to late 20s. 60 million years of time. The dinosaurs died off 65 million years ago. And amazing things have happened since that time. Even this odd little critter that Homo sapiens is. But anyway, so it's 60 million years of time, and things were so different. That is where the equator was. This is a representation of North America now. We are right here. We were north of 30 degrees south somewhere, but not too far north of that. The equator basically going through Puget Sound and East Greenland. And that's kind of like what it was. I mean, these whole things, how much things have changed over time. All right, in New York, some famous places and things. This is Taconic Falls out there in central New York around Ithaca. This is a beautiful fake hops trilobite that actually is about that large. This is Stump from Gilboa. And in fact, Neil over here, sitting in the row by himself there, he's a volunteer up there and an earth science educator. And he actually came over to my office on Thursday with a bunch of other earth science, were they all earth science teachers?
Just teachers.
Just teachers. Yeah. Anyway, and then this is what it looked like at that time. There was a smaller continent colliding with Eastern North America, like India has collided with Southern Asia over the last 35 million years to build the big Himalaya mountain range. There would have been a big mountain range. There was rock melting and coming up, explosive volcanism happening, carrying volcanic ash, even as all far west, I keep bringing it up, as Iowa sometimes. After age 8 in the second trip to the Colorado Rockies, I couldn't wait to grow up and get out of Iowa. But so out here was our seaway that was slowly being filled in by sediment as the mountain belt rose up. All right.
Was the jet stream in the opposite direction then?
Oof.
To carry the egg?
The volcanic ashes, we did paper on this built. We know of at least 100 different volcanic ash layers in the Devonian rocks in the eastern US. And actually 2 weeks ago, I found 5 more at a place, apparent ones. And I'm going to get one of them dated this winter. But anyway, this is a typical outcrop. If you've ever driven up Catskill Clove, this is on the north side of the road. Once you get above the now closed parking lot to get to the falls. But anyway, up here, the bedrock is the rock that's still attached to the earth. And the bedrock up in the mountains is chiefly sandstone, sands that were cemented together. And then I'll use the term shale loosely, basically muds, but sometimes silty or sandy also, and sometimes some thin sandy layers like this one right here. And paleosols means ancient soils. And so some of these, where it gets real rough in here, rough textured, that's a fairly mature fossil soil that trees would have been growing in, the Devonian trees, along with other vegetation. Okay, and again, looking at our environment there's the alluvial plain. You can see rivers coming down out of the mountains carrying mud, sand, and gravel. And you can see there's a broad area between the rivers sometimes. The sandstones were deposited mostly in the river channels. And then these sediments down below were deposited out on the floodplains when the floods would come. And I will tell you, without having a rock to show you the evidence or things, but at that time, being approximately 30 degrees, a little bit higher than 30 degrees south of the equator, and a time of a greenhouse climate overall, New York, the Catskill Mountains, eastern US, had a monsoonal type climate, dry season, wet season. Anyway, there's so much to talk about. So just an example of a river, the floodplains off to the side. And this is just a great example from up in Washington state right there. Here's the river channel, and it's during a flood, and all the fine sediments, the clays get carried way out on the floodplains. Anyway, all right. So this is the third section to talk now, and we are going to talk about Devonian plant life for the most part, and the Catskills fossil forests. This is a beautiful image that is supposed to be about the late part of the Devonian from the Melbourne Museum in Victoria, Australia. They have some nice images of the different times during the Devonian in their exhibits. And actually, we have artists who are building new ones, new images, drawing new images about these forests for the future exhibits in Adirondack Hall on natural history of New York. All right, this is the time when life really moved onto land for the first time, this Devonian period. And by the end of it, you even have your first amphibians, what we call tetrapods, 4 legs. And they evolved out of some of the fishes, the bony fishes that had lungs along with the ability to breathe, get oxygen from gills. And that's what they evolved out of, were some of these bony fishes. Anyway, and this is also the oldest known fossil forest in the world. Although, some new findings. All right, so looking back at this time, all these plants until the latest Devonian were very primitive. They only reproduced by spores, like ferns do now, like lycopsids, the ground pine that I see on my land and stuff, the little things that look like little trees. They all were spore bearing until late in the Devonian. At about 400, the beginning of the Devonian period, your tallest plants were only about this tall. That's it. In fact, I have a very primitive plant. We're not sure if it's truly a plant that stayed around since that time, and this is one of them right here, Psilotum, or if it was a fern that became more primitive once again. But it would be a plant like that. In my office, I was able to show students from RPI today one of these, the basic forms that these simple plants had. Chlorophyll in the stems, no leaves whatsoever yet. By 30 million years later, in our forests here in New York, we have trees. And this is a tree, a reconstruction, a drawing of a tree that came from up in the Catskills, that the entire thing was taken out of this quarry in more than 1,000 pieces and put back together by a master puzzle maker. But this would be about 30 feet tall compared to that tall at the beginning of the Devonian period. And by 50 million years after this, you had the first seeds. This is a penny, obviously. That is a seed pod, reconstruction of one of them right there from near the end of the Devonian. And actually, I was down in northern Pennsylvania at a classic site for Devonian terrestrial environments. And the paleobotanist I was with, he found 5 of those seed pods in a couple hours in the afternoon in this one layer. All right, the ancient Catskill forests. Here is the reconstruction of that about 30-foot tree all together. Here's the base. There was little bits of signs of perhaps the roots reaching down, finger-like roots reaching down into the soils underneath. It was tipped over and laying flat. Up here was the top of the tree, but you can't see much of it right there. It's hard to get a grasp of what it looked like. That's a meter, so a little more than 3 feet right there. This is a tree called Eospermatopterus. These are the famous Gilboa trees found. Even the first stump was found like 1856 or something up in the Gilboa area. So this is that reconstruction that I just showed you. Over here is the top of this tree right here. And you can see here, these patterns are leaf scars. This is strange. It has no relationship whatsoever, but the structure of this kind of tree, Eospermatopterus, is much like modern palms. Finger-like roots extending down into the soil, not the big roots that we think of so often, and then kind of a onion bulbous base, a long stem that goes up with leaf scars where the leaves have come off. And then at the top, kind of palm-like leaves. These are sticking up. This one has broken and is laying next to the tree right there. But these are the scars like you'd see on a palm tree. But again, no relationship. This is a very, very primitive tree. And again, only spore bearing. It's just a useful, evolutionary wise, it's just a useful set of structures to live on Earth with. Palm trees versus these Eospermatopterous trees. All right, and that's just showing you a reconstruction of somebody building off of what they saw there. What do you see? One of the things that catches my eye, of course, is the reddish color overall. Another thing that catches my eyes is these patterns that are often rather vertical, up and down, angling off sometimes. Ah, look at that. One becomes two. That is where roots from some of these trees penetrated down into what's one of these paleosols I mentioned, ancient soils. And you can see the roots of some trees reaching down into there. That's must be a quarter for scale. So not great big, thick roots.
Presently fossilized into rock now, I take it.
The roots,
What we're looking at here.
yeah, the roots have decayed, and with rainfall and stuff, very fine red clays that were at the surface came in and filled the holes where the roots were. So that's what you see there. So that's one of the patterns there beneath the trees. This is one of those soils that I mentioned briefly. The redder vertical lines are where the roots penetrated the soil, but the roots decayed, but fine clays, red clays came down, even redder than the background soils. The other thing is the texture is so rough too. And part of that is these lumpy textures, dirt clods. Some of that would be dirt clods. All right. You can find plant material as you're down in the Catskills region, along road cuts and places like that. But most of it is not very good. This is the impression of a log right there, another one here, another one here, another one there. Most of the stuff you would find is not very impressive. Mostly stem and root impressions. Sometimes the root traces into the red soils will be green associated with decay of the plant material. The red is what's typical in the Catskills so much. If you were, get this, you can read the water tables in the Devonian in the Catskills. If you see red, that means the water table was low and oxygen could come in and rust, oxidize the iron in there to give that red color. If the water table was high, you would get green colors to the soils and to the floodplain deposits, unless you got dark gray to black colors. And that's where you had swamp environments. And sometimes you get a lot of pyrite in some of those dark deposits, just like if you step into a mucky black swamp and you try to pull out your boot and it won't come and it smells like that strong sulfur smell. That would be from wetlands in the Catskills of 370, 380 million years ago and older. This is what you don't find so often. This is a log right here that was found in a quarry out in the southwest Catskills. The black is the actual wood material that over time under pressure and chemistry that's going on was carbonized, just turned into carbon instead of the regular woody material. But sometimes that preserves some of the nice structure of the plants too. All right. This I just found out like 4 or 5 weeks ago. Chris Berry, one of the paleobotanists, he's from Wales over in the UK, and he's one of the biggest Devonian paleobotanists globally. And he worked in the Cairo quarry a lot. He also worked in the when they uncovered the Gilboa quarry too. But what you're seeing here, some of the linear features in here are hard to make out there. That's part and counterpart. So basically you've got two sides of the same thing there. And again, that's about 1 meter. So this is a drawing of what's on there. And what you see here are plants that get this tall. I measured up to my wrist this morning when I was thinking about this. And that's 2 meters. So that would be the tallest one of those plants right there. And line drawing versus the fossils, of course. And there's a close-up of the top of one of these. And that would be right there, coming to that point, and over here to that point. And this is a reconstruction of this plant. You can see a young one there that was about a half meter tall, or maybe, you know, more than that, obviously, yeah. This was found in Germany a few years back by Chris Berry and a partner of his, Geisen, up there near the top, and they reported on this in 2013. And is this a tree? This is the question that I've heard paleobotanists talk about. When is something a tree? When is something not a tree? What's the boundary between that? So these might be considered to be 3 million years older trees, but distinctly smaller than found at Gilboa and at the Cairo quarry. All right, this is a fancy reconstruction by an artist, and this was on the cover of Nature when the paper about the Gilboa forest came out in 2012. And strange plants, these are the representations of the, quote, Gilboa trees, the Eospermatopterus, with their strange palm-like vegetation at the top. This is something different that seemed to follow along the quarry floor and then would disappear. And what it seems to be is something that's not a vine, that's not a tree, something in between. I live in the forest, so I see these young trees that get very tall because they lean in against the tree. So they don't put so much energy into their structure. Question back there.
Would the material of the, I'll say the trunks, be similar to modern wood or totally different?
I'm not going to try to answer that question. I do know that this strange one that is going along, at first they called it alligator skins because they had this coarse, like horse plates, almost looking structure to it. I don't know what the cork of the trees were like at that time. Some of the paleobotanists would know, but I can't answer. Sorry. Yeah. Yep. Anyway, Gilboa forest, of course, what's been known since the 1850s, and certainly since Winifred Goldring, former state paleontologist at the New York State Museum, when she first discovered all these trees. In fact, there's 5 levels around Gilboa that preserve some of these forests. The stumps. One of the things I didn't say about Eospermatopterus is that, like a palm, it's hollow on the inside. So these fossils here are where the trees got broke off, perhaps during a major storm or even a hurricane, and then the sand poured down and filled in where the hollow part was. Anyway, all right, and here we go. This tree here, these Eospermatopterus trees, instead of having those roots going out like we've seen already, basically they have finger-like roots going down all around the plant, all around the tree, and they form these craters like these two right here. And that's a rock hammer for scale, about that size. All right. The stumps and the vegetation were known since the 1850s, and especially Winifred Goldring's work in the 19 teens. But in 2010, just like we'd found at Cairo the year before, was they uncovered another forest floor with the places where you could stand here and you could see where the other trees in the forest stood. And this is a map of the Gilboa quarry that was uncovered in 2010 and then covered over again in 2011. The round features like that, it's not real high resolution. It's from a photo I took myself of the map in the field. But the round objects here, that's the Eospermatopterus trees. And they were the trees that really dominated that environment at that time, different from the Cairo quarry. All right, so again, a good shot of that. There's one of those craters where the Eospermatopterus trees sat. The Gilboa forest is about 2 to 3 million years younger than the Cairo quarry. And that was the big thing about the Cairo quarry. It's now the oldest known fossil forest. Again, 2 of these craters, you can see the strings stretched out that they were using to help draw that map of the forest floor that they were seeing. Here, in some cases, there are stumps and in place in the rocks sometimes too at Gilboa, but not at Cairo. And you can see how the bottom of that would sit in either of those craters, although it's too big for both of those right there. Okay, and Frank Manalini's a tech at the museum. He's the guy who found and then completely dug out that 30-foot-long tree from a quarry in the Catskills, brought it back to the museum, master abstract jigsaw puzzle worker. He was able to put it all back together. Yeah. So that's just his drawing. He's a great artist too, besides many other things. This is now the Cairo fossil forest. And what we see here is one tree and another tree. And this root that's sticking out that way that doesn't look like much right now. No, it's this one. I was walking across here and I saw a little bit of a gutter, more filled in with gravel. But that was the first thing that I saw. And it was like, I was telling Mary beforehand that my unconscious mind had a pattern of a meandering gutter from marine rocks, some features that form on the seafloor during major hurricanes and things. And it was like my eye unconsciously picked up this gutter-like feature. And this is what eventually came of all this. You can see tree roots. These are those same 2 trees. These are a couple other trees, the same type. You can also see these rings like that are the Eospermatopterus trees, including a number of small ones too, scattered around, and small trees like these larger ones called Archaeopteris. Not to be mixed up with Archaeopteryx, the first bird. Pteris is for plants. All right. Anyway, initial discovery, walking across this floor, and there were a few features like this that were kind of filled in with gravel. And my eye just happened to catch one of those. And I was looking, what is this? What is this? And Frank Manalini, who did the artwork right there, and Linda Hernick, we were there. We started looking around and they found some somewhere and we started following them. And we came to one place where 11 of these big gutters met, and it dawned on us, wow, that's where a tree stood. And for the paleobotanists who came, Dr. Bill Stein from SUNY Binghamton, who's now retired, but he's another one of the big paleobotanists for the Devonian period. When he first came, he was like, and Chris Berry when he came too, no one had seen the impressions of the roots that would tell you right where all the trees stood in a forest. So for the first time, he could stand there and look and he could see in his mind's eye where all the trees in this 385 million year old forest stood. It's one thing to find the trunks and the leaves, et cetera, but to see where each tree stood just floored those guys. I mean, it floored us, but they'd spent their careers working on these fossil trees, and to see where the trees stood in a forest was amazing. So this is what it looked like. This is what it looked like. This was the smaller tree next to the big tree that we saw already. And this is, we started doing our work. We started finding where the brick stand is where different trees stood in this forest. And that was just the beginning. Here is the big tree and the little tree. And we started the work before the research starts of just starting to brush these out. Eventually, actually the town of, it's in a quarry owned by the town of Cairo. And the highway department, they came out and just, for one thing, did one of those things that, you know, the spinners to clean the streets off and stuff. They just did that to first get down to it. And then they brought hoses out and they sprayed it down. They are hoping to turn this into a scientific preserve and an educational center and preserve it. We'll talk about that a little bit. So anyway, first thing was uncovering the fossils. This is what that looked like after some brushing, and eventually it looked more like this. You can see the roots coming out right there of the little tree. All right, again, here's our two friends, the big first discovery. This is the first root that I found, but as I said, it was filled with gravel at the time. You could just make out that there was some meandering feature there. And it was this root, as we started mapping, went out more than 24 feet before it disappeared into the rock. Now it's great because Chris Berry, who I've mentioned a couple of times, the big paleobotanist from Wales, he had just a month before this put in an abstract for an international meeting in Arizona for a paleobotanist. And he said that during the Middle Devonian, this type of tree was really pretty small with very small root systems. A month later, we found this, and by the time Chris got to the meeting, he had a very different story to tell, which was very exciting. But yeah, I mean, look at these coming to meet 11 major roots going out in all directions. All right, so this is the beginning of the research work. There's our two friends, the big one and the small one again. We've got these strings stretched out. We started mapping just, you know, with those squares, rectangles actually, and drawing a single rectangle at a time. But Bill Stein, the paleobotanist from Binghamton, he just a very creative-minded guy. And so he built this feature that put the camera out on an arm 10 feet up in the air, and he would get it here, get the camera set, remotely shoot photos, and then they would move it over about 3 feet, a meter, shoot again, and they actually covered a whole area of the initial discovery that way, using these photos together to form something like that. Well, that was a lot of work, and it still wasn't great. So Bill, he got a drone. And now he could just put it up above the forest floor and get the real geometry of things and the clarity of what things look like. It's amazing. I mean, just thinking about, for the first time, apparently, somebody who studies fossil plants from the Devonian period could actually stand there and see where all the trees in the forest live, the small ones, the big ones, etc. Was really something. Drone photos. All right. And this is, once again, the big tree. There's Frank Manalini, there's Bill Stein, and there's Linda Hernig standing around the farthest edges of the roots. I'm standing out at the edge of this one right here when we were still sweeping out the roots. Very much the opposite of what Chris Berry had put in an abstract just a month before we came across this. Anyway, 3 types of trees here. There's 3 types of trees at Gilboa also. But here there is the Archaeopteris trees, that one, the Eospermatopterus, the Gilboa trees, and an unknown tree, but apparently some type of lycopsid tree. Lycopsid trees, we'll see a picture of a modern one in a minute, were some of those that during the time after the Devonian period in the Carboniferous or sometimes Mississippian and Pennsylvanian periods, were major contributors to the coal fields in Pennsylvania and around a lot of the world. But anyway, so here is the wonderful branch at the end of an Archaeopteris tree right here, real leaves for the first time. This is an Eospermatopterus tree at the top. We've looked at that. And these are the forms that are interpreted for some of these lycopsid trees. Again, the lycopsids, all three of these are spore-bearing trees, but this is the lineage that leads to the pine trees, to the conifers and their relatives. The lycopsids, this is from up on my land, shot last year. That's fairly tall lycopsid called ground pine that you'd see in the forest. We have 3 different types of lycopsids in our forest. And eventually they mapped, here's the 2 big trees, they mapped the equivalence of 0 to 70 yards on an American football field. And that's not all. That's not all that's there. So really just an astounding find. The initial discovery was around there. All right. What's missing at Cairo that they had at Gilboa? There's not hard parts. I will say, though, as far as the sumps, but actually since the late 1950s at least, they've found, paleobotanists have gone to the Cairo quarry a lot and found things. A lot of parts of different vegetation, some of them they didn't know what connected to. But this is Gilboa. And right there is another one right there of one of the Eospermatopterus trees coming down to that forest floor that we looked across, showing where all the trees stood at the Gilboa forest. So this is at the Gilboa Dam quarry. All right, now on to the Cairo, back to Cairo again. This is what it looked like the last number of years right there, with a bunch of blocks that the highway department of the town of Cairo put around the core of the fossil forest area there. And as I said, they want to turn it into an education center and scientific preserve. And I'm trying to help them. We'll meet next week about things. They recently installed a protective boundary. They put these, do they call them Jersey stones or something? Jersey blocks, and then put poles into there and put fencing around almost all of that area in the quarry. So it's well preserved. You can't really go in there these days. Occasionally there's a trip that somebody who is a student of it all, a professional who can lead some people into there sometimes. And I'm the only one around. So that's what I do a few times a year. But there's not really stuff to collect there so much. You can't pull a block out of the 20-foot root or anything like that, impression of a root. But it is to help vehicles, 4-wheelers like to go over them and just try to wipe them out. Anyway, I'm going to leave with one more point. And it's a quiz for you. Also found in the Catskills is stuff like that. Black stuff, dark stuff. Another piece right there, where all the very delicate, fine structures in the plant are preserved. And from other sites, even nearby the Cairo quarry, actually between both of them. Any guesses? Dark stuff. Kind of chunky, although the ones up above are kind of crushed. Why am I doing this? My wife makes fun of me for all these obscure little things I do sometimes. Charcoal. Charcoal. Okay. That is charcoal. And I found that in 4 places in the Catskills and once in Western New York already, from Devonian forest fires. Lightning strikes. Remember when I talked about we had a monsoonal type climate here at that time, dry season, wet season? Something struck me about thinking about this more recently, maybe a couple of months ago. And of course, the atmospheric scientists here at Albany would know a lot about this. But there's lightning that happens during the wet season, of course, but before that arrives, there's dry lightning. And so at dry climate time, along with dry lightning that happens without the thunderstorms and stuff, led to charcoal deposits even. So wildfires, and there's only two ways that could happen. I would guess through lightning or, some time traveling geologist who started a fire while he was there, or she. Yeah. Anyway, thanks everybody. Thanks for coming.